Hey everybody, and welcome back to Patel Academy. Today I wanted to do something a little bit different from the content videos on calculus I've been doing in the past few videos, and I wanted to do a timed walkthrough of some practice questions for the AP exam. So today I wanted to go through the AP Calculus AB 2019 free response questions. And because this is a timed walkthrough, I wanted to obey the timing information set by the AP examination. So for the first two questions, I'll obey the calculators are allowed rule, and the maximum time limit is going to be 30 minutes. For the remaining four questions, which makes up part B, calculators are not allowed, and I'll set myself the limit of 1 hour. Now, I'd also strongly suggest trying to work through these questions when you do practice in less than 30 minutes, preferably 25 minutes or under, so that on the actual examination you have the last 5 minutes in order to check over your work for any arithmetic errors, which are probably the most common causes of error, more so than the conceptual errors. So let's get right into it, setting the timer. The question number one is a rate in and rate out question. As I can see, I'm given a function e, which is e at t equals 20 plus 15 sine of pi over 6t, and a loss function or a leave function L at t is equal to 4 plus 2 to the power of 0.1 t squared. Now both of them are measured in fish per hour, which tells me instantly that this is a rate of change and not a measure of the number of fish. It's a measure of the change in fish, and t is measured since midday. So the first thing I would do, even before I read part A and start solving, is to plug in these functions into my calculator. Most likely, I'll have to call upon these functions multiple times, so it's much faster to just type in, for example, the derivative of e at t, rather than the derivative of this entire function, and then later on the integral of this entire function. So question A asks, how many fish entered the lake over the 5-hour period from midnight to 5 a.m.? Give your answer to the nearest whole number. Well, this is asking about the total number of fish, not the total change in fish necessarily, or it's not the rate of change of fish. And so I immediately figure out that this is going to be the integral of this rate of change to get the original function, because the integral of a derivative function gets you the original function by the fundamental theorem of calculus. And so what I see is that I'm going to take the integral from 0 to 5 of this entering function e at t, and don't bother trying to solve the antiderivative. While it isn't that much more time consuming, it's infinitely faster, and it'll be infinitely better in the long run if you just plug it directly into your calculator as e of t instead of trying to manually do it. And so what do I get in this case? Well, I get 153.458. And then rounding, so this is 153. And remember to include units. In most of the questions, it will say include your units of your answer, but in the odd case it doesn't. It doesn't hurt to put down the word fish. Like, it's not going to take you that much longer, but it'll ensure that depending on your marker, it'll ensure that you will get the point, because sometimes it's implied but not always necessarily explicitly said. So this was a very easy part A. It's to let you get relaxed into the free response question, because later on the question will become a little bit more complex in terms of its conceptuality. This is just a simple integral. So moving on to part B. What is the average number of fish that leave the lake per hour over this 5-hour period? Well, what do we know? Well, we know that the average value of a function along an interval a to b inclusive is equal to 1 over b minus a times the integral from a to b of our function. And so in this case, we just do the same thing. We have, 1 over 5 minus 0 times the integral from 0 to 5 of, this time we're going to use our leaving function, L at t. And so when we plug that into our calculator, 1/5 times this integral, we get 6.059. fish. And so in this case, keep in mind that it didn't ask us to round, so it's better to leave it as the number you got. Now don't also put, if your graphing calculator for some reason gives you 7 significant digits, don't put all 7. Just put anywhere from 2 to 4 4 is generally the accepted maximum number of significant digits that you should be putting in. So in this case I put 4. If you put 6.06 fish, you wouldn't be marked wrong. Alright, so for part C, at what time t within the inclusive open interval 0 to 8 is the greatest number of fish in the lake? Justify your answer. Well, the easiest way I'd say that you would do this is to define your own function, which will help you actually keep track not only of what's the rate of change and what's the number of fish, but it'll also help you in the next question, jumping a little bit ahead. Normally on the AP exam, you would have read through all the questions before you started. That's generally what people do. And so you would have noticed that in this next question that I'm going to get to, you're going to need to do a similar thing. So it helps to just define a function. In this case, I'm going to define a function of the total number of fish. So I'm going to say the total fish is given by f at t, which is equal to, now keep in mind, I have the expression e at t minus L at t. But what exactly does that mean? Is that necessarily the number of fish in the lake? No, because they're both rate of changes. So that would be the instantaneous, so at any given point, the change in fish at that time. And so in order to get the actual number of fish, we have to integrate this. So similar to how we were integrating the individual functions, this time we have to integrate the difference between the functions with respect to time. And for consistency's sake, this will be done from time t equals 0 to some time t. Now, yes, in this case, it is a little bit confusing because I have t as a bound and t in the actual expression, in the actual integrand. If you were to use, for example, s in the integrand, so e at s minus L at s, the integral taken with respect to s, you would be marked wrong. In this case, I'm just doing it so that it's a direct copy from the question. So I have e at t. But as you'll see, it might be a little bit easier to use e at s just to show the fundamental theorem of calculus. Now in this case, we're trying to find the greatest number of fish, so we're going to take the first derivative. So using the fundamental theorem of calculus, I get e at t minus L at t. This is because you plug in the upper bound and then multiply it by the derivative of the upper bound, but the derivative is just 1, so all I have to do is plug in t into the actual function. So I get e at t minus L at t. Now, in this case, we're trying to find the absolute maximum. So if it's an absolute max, I have to test critical points. So these are the points where the derivative is equal to 0, and I have to test my endpoints. And so what I like to do is I like to say, okay, first I'm going to plug it into my graphing calculator, find the critical points. And so when I do that, when I set e at t minus L at t equal to 0, I get my critical point as being 6.204. That's equal to t. And so then what I like to do is I like to do a little chart. It makes it really easy to evaluate. And so in this case, this is probably why using s as your variable in the integrand was easier, so you know where to plug in t. You only plug in t into the upper bound. That's where t is. So actually, I'm going to change that just really quick and make everything less confusing for you guys. So I'm going to have e at s L at s and ds. And so in this case, for my t values, I'm having t is equal to 0, t is equal to 6.204, and 8. And so when I plug in each of these values into t, and keep in mind the easiest way to do this, honestly, is to probably have a table or copy and paste this integral multiple times and just change these upper bound values. And you get at the point 0, obviously it's 0 because you're taking the integral from 0 to 0, so the answer has to be 0. It's a lot of zeros. When you have t equals 6.204, my value of the number of fish is 135.01. And then when t is equal to 8, my value is 80.91. And so what do I get? Well, because at this critical point, we have the most amount of fish, this is our maximum. So we see there's a maximum at t is equal to 6.204. Now technically this should be enough to justify your answer, but to be on the safe side, you could say by the first derivative test or by the candidates test. And usually adding this extra sentence at the end, the maximum number of fish occurs at the time 6.204 by the candidates test. It won't hurt, it'll only help in the odd case that the marker was looking for that. So moving on, this was a pretty heavily conceptual question because it required you to not only identify and use the fundamental theorem of calculus, but also the candidates test, and to recognize the difference between the number of fish and the rate of change of fish. Question D, is the rate of change in the number of fish in the lake increasing or decreasing at 5? Well, now this is where knowing what function represents what is important. We're trying to find the rate of change as increasing or decreasing. So it's essentially the change in the rate of change. And so in this case, I'm going to define a function for my total rate of change. So I'm going to say r at t, for example. In this case, it's going to be just the simple e at t minus L at t. And so now if I take the derivative, this is just term by term differentiation, so I get e prime at t minus L prime at t. And so r prime at 5 in this case, because t equals 5. It's just e prime at 5 minus L prime at 5. And plugging this into your calculator, you get negative 10.7228. Now because this is less than 0, the function, so the rate of change, is decreasing. Now you could say by the first derivative test, this should be again enough work. Or you could say because the first derivative is less than 0, because that's just a property of the derivative. Now also keep in mind, in this video I'm using these abbreviations like ROC. As you'll see later, I'll probably use them for some theorems, but on the AP exam I would strongly suggest using the full forms, especially because when you're writing, it's not going to take that much extra time for you to write these full forms, but it helps keep your answer clear, because there is the possibility that if you do end up messing up your final answer, that they can go back and allot partial points for your work. So for example, one of the things might be, like one of the values where they can give you a point might be identifies that the total rate of change is equal to e at t minus L at t. And so in this case, if you don't specify that it's the rate of change, then you might not even get that point, even though you've stated that r at t equals e at t minus L at t, if you mislabel it. So moving on to question number 2. The velocity of a particle p moving along the x-axis is given by this function v sub p at t. We're given on this table on the right some select values with regards to t and v sub p at t. We're also given that this particle p that we're talking about at the origin is at the origin at time t equals 0. So it has a position of 0 at time t equals 0. And we also know from the table that it has a velocity of 0 at time t equals 0. So question A asks, justify whether there must be at least one time within this interval at which the derivative of the velocity, so the acceleration function of this particle, is 0. Now, in this case, when we're saying justify, you should immediately think theorems. Now, what theorems relate the derivative to the original function? Or can, because we also know that the derivative is equal to 0 when you have a maximum or a min, so an extrema. So the only two that really come to mind are the mean value theorem and the extreme value theorem. Now in this specific case, both of them can be used. I prefer the mean value theorem because it's kind of quicker at getting its point across. For the extreme value, you have to do it like within one part of the interval, within the other part of the interval, and then explain why this middle part has to have a derivative of 0, so why there's a minimum. For mean value theorem, we'll just recall that what the MVT says is that my f prime has to take on some value c such that f prime at c is equal to f at b minus f at a over b minus a for c is within some open interval a to b. And so in this case, well, we see an open interval. We see that the function is differentiable. And so it's automatically continuous. Keep in mind that differentiability implies continuity, but not the other way around. So if it said it's given by the continuous function, then you wouldn't be able to use the mean value theorem. You would have to use the extreme value theorem in this case. But in this case, because it's differentiable, it implies continuity, we can use the mean value theorem. So we say that v sub p prime at t must be, so f at 2.8, so our b value is 2.8, so that's 55, minus f at 0.3, which is 55, over my b is 2.8 minus 0.3 should go to 0 for some t in this interval, 0.3 to 2.8. Now I am using the interval notation. I am using the set notation. You can use the interval notation as well if you want. It doesn't matter as long as you get your point across that we use the mean value theorem, which is the justification, and we proved that the derivative to the acceleration has to be 0 at some point. Alright, so moving on to part B. It says use a trapezoidal sum with the 3 subintervals to approximate the value of 0 to 2.8. Now in this case I have copied the table again so that we can use the exact values. On the actual AP exam, it's going to be directly above the question, so it's going to be on that same page, so you will be able to refer to it again and again. A trapezoidal sum. Well, keep in mind, now this might be a little bit of like a geometry review. You guys should know this, but the area of a trapezoid is given by our height times our base 1 plus base 2 divided by 2. Now in this case, keep in mind that if we have some curve, right? So if we have some curve and we're trying to take the trapezoidal sum, this is our height, so it's the interval that we're using. Our base 1 is going to be f at our first value. Our base 2 is going to be f at this value, and then our height is going to be equal to b minus a in this case. And so we basically just have to keep adding up these trapezoids until we reach from the lower bound to the upper bound of the integral. So we can say that the integral of from 0 to 2.8 of v sub p at t with respect to time, the integral with respect to time, is approximately equal to, not equal to in this case because it's not it's not the limit trapezoidal sum. So it's approximately equal to, well in this first interval, our b minus a, so our height is going to be 0.3. Our base 1 is going to be the function at 0.3, so 55, plus 0 over 2, plus, in this next interval, is going to be 1.4 times, well, now we have negative 29, plus 55, over 2, and then plus this final one, which is 1.1 times, now we have 55 minus 29 because it's plus negative 29 over 2. Just put a little squiggly line over here so we don't get confused. And so when you put this into your calculator, keep in mind we're still in the calculator question, or you can do this by hand. These ones shouldn't be as hard to calculate, but sometimes just to save time, to ensure that you're saving time and they're still going to be accurate, you plug these into your calculator and then you get the final value of 40.75. And so that's our approximation. Now in this case, it doesn't say to interpret our result or interpret the integral or anything like that. So all I'm going to say is that the trapezoidal sum value is 40.75. If we were asked to identify exactly what this meant, then I'd say this is 40.75 meters traveled. Because ultimately what this integral is telling us is how far, what's the change in the displacement. So the integral of velocity becomes displacement. What's the change in displacement from time is equal to 0 or 2 time is equal to 2.8. Now in this specific case, because we are given that the position at time 0 is 0, you could also interpret this as it's the position at time t equals 2.8 is 40.75. So both interpretations match. Moving on to question number 2, part C. A second particle q has a velocity equation given, and it's between the time interval 0 to 4. So we're trying to find the interval during which the velocity of this particle is at least 60. Now, if we plug in this into our calculator, if we plug in v sub q at t, and then we solve it to equal to 0, we get the following critical points. Or not critical points, we get the following roots. The first one is 1.866. Our second one is 3.519. So now in this case, now that we have our two roots, you can verify them on your calculator, we notice that both of them are within the original interval from 0 to 4. Now also, we need to consider the fact that this is where the velocity is at least 60 meters per hour. Now you could verify this with a derivative or with a quick plot of the graph, but between this interval, the velocity is going to be larger than 60. And so we're trying to find v sub q of t as being greater than or equal to 60. And this lies within this interval, not from the endpoints to these critical points. So why does this matter? Well, now that we have our critical points, all we have to do is that our distance, it's the integral from 1.866 to 3.519 of our velocity function. Now, technically there should be an absolute value of the velocity function for questions like this. In this case though, it being greater than or equal to 60 meters per hour, we don't necessarily need the absolute value. So I'm going to put it in here just for completion's sake. The reason being that this is the general formula that you would do is you would put the absolute value to allow for, in case if the velocity does go negative, if it said like it's less than, it's at most 60, and then the velocity actually did go negative, then you need to do the absolute value. But because it's the distance traveled, oh, and that's also it, because it's the distance traveled, so the negative component should be accommodated as positive in the integral to allow for the calculation of distance instead of displacement, sorry. And so find the distance traveled by the particle q. Well, when I plug this into my calculator, I get 45.9376. Now keep in mind what I said about significant digits. I generally like to round these off to at max 4. In this case 4 makes sense. So 45.94, and in this case remember to include meters. Alright, so this was recognizing that distance is the integral of the absolute value of the velocity. In this case, however, the absolute value isn't necessary because the velocity is only positive and the displacement is also going to be only positive within this interval. Alright, so moving on to part D. Now this is the last part of the questions in part A. So after that, we'll be moving into the no calculator part B section. So in this case, it says that at time t equals 0, particle Q is at position x equals negative 90. Using the result from part B and our function, approximate the distance at time t equals 2.8. Well, immediately a formula comes into mind that you guys should probably know when you're relating velocity and distance, is that some distance, our distance x, is equal to x of 0 plus the integral from 0 to some value t of v sub q. In this case, I'm going to do it like our first question. I'm going to say s ds, but if you put a t there, it's not wrong. It just makes it a little bit confusing if you were to use like the derivative. In this case, you don't necessarily have to take the derivative. Now remember that for our particle p, our position at 0 is just 0. So our distance, I'm going to label that x at p. So our position at p is equal to just the integral. In this case, it's v. And we found that out in part B as being 40.75 approximately by our trapezoidal sum. Now for particle Q, x at q is equal to x at 0 plus this same integral. In this case, I'm going to use vq at t just because we don't have a t, but in the general formula I used s. Please don't get them confused. Now we're given that particle q is at position x equals negative 90, and then plus this integral, our overall thing, we get 45.93. 937. And so our distance is just x at p minus x at q. Now in this case we would take the absolute value because we don't care about which one's higher than the other, we just want the net distance. So the distance becomes 5.188. So that's our answer. And so it's just knowing this first formula, I'll put a star beside it, that helps relate position and velocity that you should know in order to solve this question. Alright, so moving on into question number 3. Now how long have we spent? We've spent a total of 27 minutes and 30 seconds to go through part A. Now the limit was 30 minutes, but keep in mind I'm also trying to explain questions, and so you guys would probably, if you were working at that pace, you guys would probably be done within, I'd say, about 20 minutes or so. So even going a little bit slower than that, you would be fine. And so don't feel worried if you didn't get all the way through part 1, through question 1 and question 2, if you're working through that. You do have time to practice, and we were going at a pace that involved repeating stuff or restating concepts. So you guys will be fine for the AP exam. So moving on into part B, I'm putting the calculator aside now. This graph that we're seeing, immediately I think of geometry. Why? Well, I see lines, so I see triangles, which I can calculate the area of. I see a trapezoid in the middle. I'll actually label it using the color black. Actually, no, I'm going to use the color blue in this case. I'm going to label this. I have a trapezoid in the middle. And then this red area that I'm labeling, I don't know if you noticed, but it's just the area of a square minus the area of a quarter circle. And so that's going to become important because I already see integral signs. And so in this case, with no calculator, it's going to heavily rely on geometry. All right, so I see reading the question that it's a continuous function, as we can see over here on this closed interval. The figure above shows a portion of the graph of the function consisting of 2 line segments and a quarter of a circle, as we discussed earlier. We also are given this exact point, 3 and then 3 minus root 5. Alright, so our first question asks for the integral from negative 6 to 5 of this function. We're given that that's 7, and then we're trying to find the integral from negative 6 to negative 2. Already, what can I judge? Well, I can judge that the integral from negative 6 to positive 5, of f at x is equal to, we can split the integral up. So from -6 to -2 of f at x dx plus the integral from -2 to 5 of f at x dx. Well, why does that help us? Well, it's because this graph has given us the geometry, the shapes needed to calculate this integral from -2 to 5. And so we have 7 is equal to, I'm going to label this with some value, I'm just going to call it alpha, just so that it's a variable, it's easier to look at in the equation than where you're writing this integral constantly. And then what do we have over here for this integral? Well, I'm going to, in this purplish color, indicate what has the exact same area. So this triangle and this triangle will cancel out, because remember that above the x-axis is going to be positive area and below the x-axis is technically going to be negative area, so those will cancel. And then in green, I also note that that small triangle and that small triangle will cancel out. So we're left with just the area of this trapezoid, which has, I'm going to mark this in this orangish color. I'm going to say that there's an h equals 1. My first base is 1. My second base is 3. And so my area is equal to 1 plus 3 is 4 times 1 divided by 2, which is 2. And so I get plus 2. And then plus the area of this, the area underneath this quarter circle, which is just this 3 by 3 square minus the area of this quarter circle. So I get 9 minus 9 pi over 4. And so I get my alpha value is equal to 9 pi over 4 minus 4, just using algebra. No need to simplify this, get a common denominator. This is all you need. Moving on to question B. Evaluate this integral. Alright, so just really quickly, I'm going to say that this integral can be split into its two components. So I get f at x dx plus the integral from 3 to 5 of 4 dx, which is equal to, now keep in mind that the integral of the derivative by the fundamental theorem of calculus is the original function. This is going to be evaluated from 3 to 5. Now the integral of 4 is going to be 4x, evaluated from 3 to 5, and no need for the constant c because it's a definite integral. Now what is f at 5? F at 5 here is 0, so I'm going to have 2 times 0 minus. Now what was the point at 3? Well, if you go back and you notice, the point at 3 is 3 minus root 5. So this is 0 minus 3 minus root 5, then plus 4 times 5 minus 3. So what is this going to be equal to? Well, I see it's going to be 2 root 5 minus 6 plus 8, which is equal to 2 plus 2 root 5. That is your final answer. Alright, that was just crunching through and using the fundamental theorem of calculus. Part C. The function g is given by g at x is equal to the integral of from -2 to x of f at t. Find the absolute maximum. Alright, so immediately with the absolute max, I know to use the candidates test and test, as we saw earlier, test crib points and endpoints. Okay, so I see g prime at x is equal to, now by using the fundamental theorem of calculus, this becomes f at x. When you multiply by the derivative of the upper bound, it's just 1, so it stays f at x. And so we're trying to find where is f at x equal to 0. So our critical points. Alright, so I see 1 at -1. Now this one, you could calculate it by using the slope of the line. So my slope of the line is 2. In this line from 0 to positive 2, my slope is 2, which means that that point where it hits 0 is going to be 1/2. And then I also see 1 at the very end at 5. So once again, I like to make my table. So I need to test, oops. my endpoints and my critical points. So I see -2, -1, 1/2, and in this case, one of our critical points is an endpoint, so 5. Now, working at the numbers over here, well, if we take the integral from -2 to -2, well, we get 0. From -2 to -1, I see a triangle. I have height 1, I have base 1, so it's 1 times 1 divided by 2, which is 1/2. The integral from -2 to positive 1/2, well, I see these two triangles that we pointed out earlier. This first two will cancel, so I just have this negative triangle. It has a base of 1/2, a height of 1, so the total area will be -1/4. And then this overall integral, well, we found that out earlier to be 11. Sorry, we found out that the integral from -6 to -2 was our 9 minus 9 pi over 4. If you just go through these numbers, though, you get the value of 11 minus 9 pi over 4. Because we just add the original 7 back. So, what can you see? Well, I see a negative and I see a 0. Clearly, those are not going to be the largest. It's a matter of 11 minus 9 pi over 4 and 1/2. Now, keep in mind, pi is 3.14 ... It's less than 4. So pi over 4 as a fraction is going to be less than 1. Well, what does that mean? 9 times a fraction less than 1 is going to be less than 9, right? It's going to decrease in its value. And so the 11 minus whatever that is going to be definitely larger than 2. And 2 is definitely larger than 1/2. So we can easily point out that this is the maximum. And so the absolute maximum value of G is 11 minus 9 pi over 4. And justifying your answer, you just say that you used the Canada's test. All right, question number D. Take the limit as x approaches 1 of 10 to the power of x minus 3 f prime of x over f of x minus arctan x. Now in this one, people might immediately jump to saying, oh, this is an AP Calculus exam. They probably want us to immediately use L'Hopital's rule. Please don't. Please always check first if you can substitute. Especially check the denominator. I see f at 1 exists, it's 1. I see arctan of 1 exists, it's pi over 4. 1 minus pi over 4 is not 0 in the denominator, so automatically L'Hopital's rule is cancelled out. But what indication that also gave me was that I can probably just do a direct substitution, right? So this limit can be equated to 10 to the power of 1 minus 3 times f prime at 1 over f at 1 minus the arctan of 1. So what is this? Well, this is 10 minus, now the slope at 1, remember we calculated this earlier, the slope is 2. You can verify that with rise over run from 0 to 2. So it's 3 times 2 over 1 minus pi over 4. What does it give us? Well, it's 4 over 1 minus pi over 4. Easy. Please leave it just like that. Do not try and simplify it. You'll waste unnecessary time, and especially in this last crunch where you have 1 hour for 4 questions, that's 15 minutes per question. Each question has at least 3 parts. So you're approximating something around about 5 minutes per part. Do not try and unnecessarily simplify if that means that you have time at the end to check. Question number 4 now. A cylindrical barrel with diameter of 2 feet contains collected rainwater, as shown in the figure above. The water drains out through a valve not shown at the bottom of the barrel. The rate of change is given by dH by dt is equal to -1/10 times root h. Now root h is measured in feet and time is measured in seconds. We're also given that the volume is pi r squared h. Now what's important here? Looking at this diagram, which they gave us, it might help to think about the fact that only the height is changing. The radius isn't changing at all. So radius is 1. Always. And so looking at this, my volume becomes from pi r squared h, it actually just becomes pi h. Sorry, give me 1 second. PowerPoint crashed on me there. So dv by dt is going to be equal to just pi times dh by dt. Just implicit differentiation with respect to time. Alright, so what I also know is that dh by dt is equal to negative 1/10 root h. So if I evaluate this at h is equal to 4, I just get negative 2 pi over 10, because 4 root of 4 is 2, so I get negative 2/10 times pi, so negative 1/5 pi, or negative pi over 5. And indicate units of measure. Well, keep in mind over here that we're trying to find the change. It's a rate of change, and so volume is measured in feet cubed in this case, right? Because our monolinear dimensions are feet, so our cubic dimensions are going to be feet cubed, and then it's measured in seconds, the time, so it would become negative pi over 5 feet cubed per second. Alright. This idea of r is always going to be equal to 1 is going to be important in simplifying questions. When the height of the water is 3 feet, is the rate of change of the height of water with respect to time increasing or decreasing? Okay, so once again, this is the idea that ROC behavior, so increasing or decreasing, use second derivative. Okay, so what did we have? Well, we have that dh by dt is equal to negative 1/10 root h. So d squared h by dt squared, is the second derivative, is equal to negative 1/10 times, well, the derivative of this inside is going to be 1/2 root h, 2 root h being all in the denominator, times dh by dt. Because once again, we're taking the derivative with respect to time. But we can again substitute dh by dt, so we get negative 1/10 times 1/2 root h times negative 1/10 root h. Now, they give us that the height of the water is 3 feet, but does that really matter? Because these root h's will just cancel out. This root h and this root h will just cancel out. And so what I'm left with is just positive 1/200. And this is greater than 0. So we can say that it's an increasing rate of change. And then once again, you can say because the derivative of the rate of change, or the second derivative of height with respect to time, is positive. At time t equals 0 seconds, the height of the water is 5 feet. Use separation of variables to find an expression for h in terms of t. Separation of variables. So we automatically think differential equations. We automatically think we integrate both sides. Both sides have to have the same variables, or generally one side will have all of the variables, in this case h related, and then the other side will have the constants that will integrate to get time. So what do I have? Well, I have dh by dt is equal to negative 1/10 root h, so 1/root h dh is equal to negative 1/10 dt. This is my separation of variables. I brought the root h over, so it becomes 1/root h, and then I brought the dt over. Now, we're going to integrate both sides, so I'll use orange. Alright, and so we get the integral of 1/root h becomes 2 root h. The integral of 1/10 becomes 1/10 t, and then plus c. Remember, we need to include this constant of integration only on one side, because if we include it on both, we get plus c plus c. These are different c values. When you combine them, you just get another constant. So it's easier to just write it once. Now, we evaluate this expression at t equals 0 and h is equal to 5. So we get 2 root 5 is equal to negative 1/10 times 0 plus c, and so c is equal to 2 root 5. So going over here, I get the expression that 2 root h is equal to negative t over 10 plus 2 root 5. And thus, I get root h is equal to negative t over 20 plus root 5. And then h is equal to negative t over 20 plus root 5 all squared. Now you can leave it like that, you don't have to expand it. That's the separation of variables. This is just, do you know how to solve a differential equation? Question number 5. I see area. This is probably the hardest, I'd say, topic, integration applications, because of how conceptual it has to be in terms of what you put where, which function you put where, especially if it's a region bounded by two different functions. So I see that I have a function g at x equals negative 2 plus 3 cos times pi over 2x, and h at x equals 6 minus 2 times x minus 1 squared. Now the graph doesn't label it. If you didn't know that h at x was the higher one, you can just plug in the value of 0 into h at x. So I get 6 minus 2 times negative 1 squared, so I get h at 0 is equal to 4, and thus I immediately know that this top function is going to be h at x, and thus this bottom function is going to be g at x. Alright, so find the area of R. Well, this is a fairly simple question, because when you're finding the area, all you have to do is the integral between, now in this case they're both expressed as a function of x. I also see that the region is bounded by the y-axis, so x equals 0, and the line x equals 2. So I get the integral from 0 to 2 of h at x minus g at x dx, which is equal to the integral from 0 to 2 of negative 2 plus 3 cosine pi over 2x minus, oh sorry, I flipped the order on this one. In this case, our h at x is going to be 6 minus 2 times x minus 1 squared, and then minus negative 2 plus 3 cosine pi over 2x dx. So this is equal to, well, I'm just going to take the entire integral first, so I get 6x minus, now x minus 1 squared, add 1, divide by the new power, so I get minus 2/3 times x minus 1 cubed. Now I would divide by the derivative of the inside as well, but because the derivative of the inside is 1, doesn't matter. Now keep in mind that we're dividing because this is the inverse chain rule, so if you're doing the chain rule, then you'd multiply by the derivative. Because we're integrating, it's the inverse chain rule, so you divide. And then minus negative 2x plus, now keep in mind that the integral of cos is positive sign, so that's why we keep this plus. Now I'm going to get sine of pi over 2 times x, but then I have to divide again because of this inverse chain rule by the derivative of the inside. Now if I'm dividing by the derivative, which is going to be pi over 2, then I'm going to be multiplying by 2 over pi. So I get plus 6 over pi sine of pi over 2x. And then not a dx because I just took the integral. So now I have to evaluate this from 0 to 2. Alright, now I'm just going to do a little bit of cleaning up. So this negative 2x will become plus 2x. So I get 8x minus 2/3 times x minus 1 cubed. And then minus 6 over pi times sine of pi over 2x. Earlier from 0 to 2. I'm just doing some quick math in my head. Okay, so x equals 2, so I get 16 minus, when I plug in 2, I get 2 minus 1 is 1 cubed, so I get 16 minus 2/3, and then minus, when x is equal to 2, I get pi over 2 times 2 is pi, sine of pi is 0, so minus 0. So I get 16 minus 2/3 in this case, and then minus when I put in the 0, 8 times 0 is 0, I get x minus 1, so 0 minus 1 cubed will become negative 1 times negative 2/3, which would become positive 2/3. And then minus, this expression will again go to 0 because sine of 0 is 0. So I get minus positive 2/3. So in the end, I get 16 minus 4/3, which is equal to 44 over 3. Now in this case, I'm not exactly sure if it would be okay to leave it at 16 minus 4/3. It might be, but that is an example of where simplifying it is definitely not hard at all. And so in that case, I probably would. So you get a nice clean answer of 44 over 3. All right, moving on to this next part. The region R is the base of a solid. For the solid, at each x, the cross-section perpendicular to the x-axis has area A at x is equal to 1 over x plus 3. Find the volume of the solid. All right, this is extremely easy because they give you the cross-section. And so we know that we're still taking the integral from 0 to 2. But now because we have the cross-sections, we know that they're perpendicular to the x-axis. So on this diagram, I'm just going to show you what the cross-sections would look like. So it'd be something like a rectangle like that, some rectangle like that, some rectangle like that. And so think about what we're doing. We're given that the cross-section of each of these has area A at x. So we're essentially taking the sum of A at x. And so, sorry, I'm going to write that down just below so that it's a little easier to read. So we're taking the sum of A at x. And so what is that? Well, that's just the integral of A at x, the infinite sum. And then we're taking this with respect to x, so we get the integral from 0 to 2 of 1 over x plus 3 dx, which is equal to, instantly you should think ln of absolute value of x plus 3 divided by the derivative, but the derivative of the bottom is just 1, so it stays as ln of absolute value of x plus 3, and then evaluated from 0 to 2. I get ln of 5, no absolute value needed because 5 is positive, minus ln of 3. And then in this case, I like to use my log properties to combine this and get a final answer of ln of 5 over 3. Very simple question. People often think that volumes are extremely challenging. Sometimes they can be conceptually. This next question especially will be conceptually. But for this particular example where you're given the cross-sectional area, it's an extremely easy problem. Extremely free marks. Alright, part C. Write but do not evaluate an integral expression that gives the volume of the solid generated when r is rotated about the horizontal line, y equals 6. I'm just going to tell you off the bat that if you get a very easy to evaluate integral, 90% of the time there's going to be some error in it. There's a reason why they're not making you evaluate it, because it would take too much time. Alright, so let's think about what happens if we're rotating a volume about a horizontal line y equals 6. Keep in mind that this horizontal line is going to be somewhere, I'll draw it on the graph, just have an orange, right there. And so if we're rotating about this, all of a sudden, even though h was the larger function, in this case g at x would become the outer, and this would become the inner. H at x would become the inner. And so what we notice is that the general formula, this is probably a formula that you should know if you're rotating, because most often you get functions rotated about a horizontal line or a vertical line, and then this is very common. So it's the integral, once again from 0 to 2, because our volume will still be capped from 0 to 2, of, in this case, I'm going to take, I'm going to take my outer, so in this case it's going to be g at x minus this axis squared, minus here, and and then minus h at x minus this x's squared. Now in this particular case, I'm going to point out that sometimes you'll see the formula where the 6 and the function is switched around. Keep in mind, because it's in the squared, if I factor out a -1, I get that switched around value, but the -1 squared is just 1. So they're going to be equivalent. And that's why you'll oftentimes see that the function and the axis are switched around in terms of their subtraction. Just know that they're equivalent. I believe sometimes the AP also does it the opposite way, where it's 6 minus g at x, but the expressions are still equivalent. Now, if you do feel a little bit uncertain and want to follow that, that's perfectly fine. This is just a formula that I've learned, where it's the function minus the axis squared, and then minus the function minus the axis squared. If you prefer the other way, go for it. You'll still get full marks both ways. In this particular case, I'm not sure whether they want us to write out g at x and h at x. I'm pretty sure that if you just leave it like this, it's fine. Also keep in mind, sorry, I almost forgot it. You need to multiply by pi in the front. Please don't forget that mistake like I just did there. It's pi times this integral. But yes, the axis flip doesn't matter. I'm pretty sure if you leave it like this without plugging in the values of g at x and h at x, you should still get full marks, because it does say do not evaluate, and once you plug it in and start simplifying, it's not a challenge to evaluate. So, a decently long expression, and this is what I mean by if you have a really short expression, then you probably did something wrong. So let's say if you just did g at x minus h at x all squared, that's a little bit too short for you to not evaluate. So I would just check again and make sure that you did everything right, but once again, it's only about 90% of the time, so there is a chance that you did get it right. So stay sure to yourself, don't doubt yourself too much, but just keep in mind that not evaluating is generally with more complicated expressions. That was a very simple question though, only a one-liner. Question number 6. The functions f, g, and h are twice differentiable. G at 2 equals h at 2, which equals 4. And then we have a line, which is tangent to both g and h at x equals 2. So find h prime at 2. Well, what is h prime at 2? It's the slope of the tangent, isn't it? And aren't we lucky that we got the exact formula for the line, and so we can instantly figure out that our slope, m, is equal to 2/3. And so, free marks once again, the answer is 2/3. We're given the answer in the question. Part B, let a be the function given by a at x is equal to 3x cubed times h at x. Write an expression for a prime at x, and find a prime at 2. Alright, so a at x is equal to 3x cubed h at x. So a prime at x is equal to 3 times, now taking product rule, I have 3x squared h at x plus x cubed times h prime at x, which is equal to, now factoring this 3 in, I get 9x squared h at x plus 3x cubed h prime at x. And so a prime at 2 is equal to, well, if we plug in 2 squared is 4 times 9, which is 36, times h at 2, well, we're given that h at 2 equals 4, so 36 times 4 is equal to 144, plus, now 2 cubed is 8 times 3 is 24, and then h prime at 2 we just figured out was 2/3, so we have 24 times 2/3, which is 48 over 3, which is 16. So I get my final answer as being 150. These are math things that you should be able to do in your head very quickly, so I would suggest trying to evaluate whenever possible these things in your head. Don't resort to a calculator, because otherwise on the AP exam, when you can't use a calculator, these arithmetic things will take longer than they should, and you will run out of time. I'm going to give you guys a quick time update right now because I'm almost done. There's only, I believe, 2 more parts to question 6 and then we're done. I'm currently at the hour mark. Keep in mind that the total exam is an hour 30. So I'm currently 30 minutes ahead. Now in some of these, I did go a little bit faster without explaining, so I will, on the questions that I think were a little bit more challenging, I will actually go back and just give a brief explanation again of why they were. And in the description, I'll just put the timestamps of the question so you don't have to listen to each of these explanations again if you understand exactly what I did and why I did it. But an hour means I have 30 spare minutes. So let's say if I split that up into about 5 minutes, and once I get to do these next two questions, I'd say about 10 minutes left. That's really good time for you to be able to check. That's more than enough time for you to be able to check through all your questions and make sure that you did all your arithmetic correctly. So we're making really good progress. Question number C. The function h satisfies h at x is equal to x squared minus 4 over 1 minus f at x all cubed for all x's not equal to 2. It's known that the limit as x approaches 2 of h at x can be evaluated using L'Hopital's rule. Use that limit to find f at 2 and f prime at 2 and show the work that leads to your answer. Okay, well, if you remember earlier, I'm just going to go back. It says that h is a twice differentiable function and h at 2 equals 4, right? Alright, so what do we know then? Well, if h is differentiable, that means that it's continuous. So that means that the limit as x approaches 2 of h at x is equal to h at 2, which this has to be equal to 4. This is the first connection that you need to make. The next connection that you need to make is that the limit as x approaches 2, being h at x, can be evaluated using L'Hopital's rule. Well, L'Hopital's rule can only work when the limit is 0 over 0 or infinity over infinity. Now in this case, if I plug in 2 into my numerator, right, x squared minus 4 becomes 2 squared minus 4, which is equal to 0. And what does this mean? Well, this means that 1 minus f at x all cubed has to be equal to 0. And so f at 2 in this case, because my x is 2, has to be equal to 1 for this to be true. Alright, so I figured out what f at 2 is equal to by my show the work or justify would be by the definition of L'Hopital's. Alright, and then, kind of like the part 2 to this question, finding f prime at 2. Well, if we have the limit as x approaches 2 of x squared minus 4 over 1 minus f at x all cubed, well, by using L'Hopital's rule, we get the limit as x approaches 2 of just 2x over negative 3 f at x squared, and then using the chain rule, we have times f prime at x. Well, plugging in 2 now, because we can, you're not going to get 0 over 0, I get 4 on the top over negative 3 times, keep in mind that f at 2 was 1, so I have 1 squared times f prime at 2, and this is, we found out at the start, equal to 4. Because of the definition of differentiability, meaning continuity, and the definition of continuity suggesting that the limit and the function have the same value. And so by doing some quick algebra, get that f prime at 2 is equal to negative 1/3. And so this is probably one of the most challenging ones on this FRQ set, because it involves not only identifying what the definition of L'Hopital's rule involves, which is 0 over 0, infinity over infinity, it also indirectly implies that you have to use the ideas of differentiability and continuity in order to identify exactly what that limit is actually equal to, because it doesn't give it to you. And then the final question in this FRQ set. It's known that g at x is less than x within this interval. It's also known that we have a k at x between g at x and h at x. Now, why was this question so special? Well, what does this inequality remind you of? Where have you seen it before? Well, we just talked about limits. This very closely resembles the squeeze theorem, doesn't it? We're asked to find, is k continuous at x is equal to 2? Well, once again, what does continuity imply? The shorthand definition is that the limit as x approaches some value t of f at x is equal to f at t. Now you could use k, except k is the function over here. You could use n, it doesn't really matter. Just use t quickly because we've used t so much. But this implies also that both things exist. Right? So we have the function existing and we have the limit existing. Now in this case, let's first talk about the function. That's a little bit easier. We know that g at 2 is equal to h at 2, which is equal to 4. Now if g is less than or equal to k, which is less than or equal to h, but g is equal to 4 and h is equal to 4, then k must be equal to 4. Right? So k at 2 equals 4. So we've now proved that this exists. Otherwise, this inequality wouldn't be true for the interval 1 to 3. Alright, so that's essentially part 1 of the squeeze theorem, you can say. That's squeeze theorem not of the limit, but of the existence of the point, or what the value of the point is. Now we move on to squeeze theorem part 2. Alright, so the limit as x approaches 2, so that's a terrible x. The limit as x approaches 2 of g at x. Now keep in mind that the same idea of differentiability implying continuity exists, and so this is equal to 4. Similarly, as we proved in the last part of the question, the limit of h at x as x approaches 2 is just h at 2, which is equal to 4. And by the squeeze theorem, the limit as x approaches 2 of k at x must also be 4. And in this case, I just wrote it in that it's equal to k at 2. And so then, by the definition of continuity, k is continuous at x equals 2. Alright, and that marks the end of the 2019 AP Calculus AB free response questions. Now, I did this in a grand total of 1 hour and approximately 10 minutes, considering how I did go a little bit fast with explaining everything in one part. But 1 hour and 10 minutes, approximately 5 minutes at the start I saved, which means that I saved about, 15 minutes in this next section? So that's really good timing for something like this. Now, some of the important questions that I wanted to go over was especially these last two. So just to make sure that you understand, this one, L'Hopital's rule can only work when the limit L, when you evaluate it, is 0 over 0 or infinity over infinity. And so something like this, problem solving strategy, is quite uncommon, but it is important to know that you can use this condition to actually solve. Because we found out that the top was 0, for L'Hopital's rule to work, the bottom has to be 0. And so we can figure out what the function is, and then we use the definition of differentiability. Remember, differentiability implies continuity to solve for the other value, f prime at 2. So hopefully you guys understand that. For this question, keep in mind that the squeeze theorem is a thing. It's something that's often glossed over in terms of when you're learning limits. Limits is often one of the first units you learn, and so people often forget. It's important to revise even the smallest things like this because questions might come up. And then finally, I'm just going to try and go back to, what was the question? Oh, also one of the other things that you should probably know is that indeed rates of change are the first derivative. If you're trying to find whether the rate of change is increasing or decreasing, it's the second derivative, which implies the first derivative of that rate of change. So keep in mind very carefully, read the questions very carefully as to whether it's giving you the rate of change or the actual value of the function. And then this one I just wanted to go back to very quickly to analyze that even though in the previous two parts of the question, our h at x, that top function, the top parabola, was indeed the top or the higher function, the larger function. In this case, because we're rotating about y equals 6, now we have to consider about what actually becomes the outer surface and the inner surface. Because keep in mind that what'll happen is when you rotate it, you'll get some figure that looks, this is just an approximation, this is nowhere how it's actually going to look, but you're going to have some sort of a circle, which is going to be our g at x in this case, or the outer. And then on the inside, you're going to have something else that models, sorry, that's not a good color to use. I can use orange. I'm going to have something else that looks something like this, for example. This is nowhere resemblant of the actual picture. I'm just giving you an example, and this is going to be h at x. And then when we're trying to find the volume of this, right? Well, what actually is the volume? Well, the volume is indeed this part, the part enclosed by both of these revolution volumes. I guess you can call them volumes of revolution. And so that's why it's important to identify what your inner and what your outer is, because in this case when you're rotating, this h at x becomes this inner yellow function, while g at x, that becomes your outer red function, and that's what you have to do, the g at x minus axis squared and then minus the inner h at x minus axis 6 squared. And then keep in mind, I did forget the first time, always keep in mind you're multiplying by pi. Why? That'll be covered when I do my integral application questions video, so be sure to check that out. However, the pi is involved with the cross sections, calculating the area of the different cross sections, and then finding the integral, so summing them all up to get the total volume. So those are the main questions that I felt required a little bit more clarification. Otherwise, remember, feel free to leave a like and comment down below. Any other questions you have, I'll be happy to answer. Any other suggestions you have on content to cover. My goal is to go through the BC free response questions and then start working again at the content, so integration applications and then the differential equations unit. And remember to subscribe and hit that notification bell so you guys can see my next video. Big thank you to everyone for your support to the channel, and I will see you guys next time on Patel Academy.